Titans. Learning to memorize at test time asks what happens when a language model can keep changing a separate memory while it reads. Attention stays precise for the current chunk, while learned memory carries selected information from much earlier chunks. Imagine processing a book one section at a time. Standard attention compares every token with other tokens inside the visible section, but information outside the context window is unavailable. Making the window larger preserves more detail, yet attention cost grows quickly as the number of tokens increases. Recurrent models offer the opposite trade-off. They compress everything seen so far into a fixed size state, which is cheap to carry forward but can blur precise details. The paper treats attention as accurate short-term memory and adds a separate learn module for compressed long-term memory. This long-term memory is itself a small neural network. Its weights are the stored state. The model turns incoming information into a key and a value, then trains the memory so that presenting the key later reconstructs the associated value. If the memory already predicts a token well, its error is small and the weights barely change. An unexpected token creates a larger error, so the memory receives a stronger update. Momentum keeps useful update directions, while weight decay gradually removes information that is no longer reinforced. Figure 2 shows the main memory as a context design. The center lane holds the current token chunk. The top lane is contextual long-term memory that changes as the sequence arrives. The bottom lane is persistent memory, learned tokens that store fixed knowledge about the task. A long sequence is divided into manageable chunks. When a new chunk arrives, it becomes the current context. Everything before it is not copied into attention. Instead, earlier information has already been compressed into the neural memory weights. The current chunk creates a query for long-term memory. The memory uses that query to produce a small set of retrieved representations related to the current topic. This gives attention useful history without rebuilding an attention matrix over the entire document. A second set of learned vectors is placed at the start of every chunk. These vectors do not depend on the current document and remain fixed while the model is generating. They provide stable task knowledge, similar to learned prefix tokens that attention can always read. The input to attention is now 3 pieces placed in order: fixed learned memory, retrieved long-term memory, and the current tokens. Standard causal attention processes this combined sequence, so each current token can use precise local context plus selected information from the past. After attention, the output serves 2 jobs. It produces the representation passed forward by the model, and it updates neural memory for the next chunk. Because attention has already combined current and historical context, it helps decide which new information is worth storing. The 3 lanes behave differently while text is generated. The core model weights stay fixed and use the tokens visible in the prompt. Persistent memory also stays fixed. Only the contextual neural memory keeps learning, so the model can form a compressed record of this particular sequence. The paper also tests 2 alternatives. Memory as a gate runs sliding window attention and neural memory in parallel, then combines their outputs with a gate. Memory as a layer runs memory first and attention second. The main context design lets attention directly choose when retrieved history matters. Updating memory token by token looks sequential, but the paper rewrites much of the work as matrix multiplications and parallel calculations within chunks. That makes the memory compatible with modern accelerators, although the exact update rules and chunk size still create an efficiency versus detail trade-off. The reported experiments cover language modeling, reasoning, genomics, and time series, with long context tests beyond 2 million tokens. The mechanism is still selective compression, not perfect storage. Useful details must survive memory updates. The core trick is precise local attention connected to weights that keep learning from the long past.